Our solar system is not a quiet, isolated neighborhood, sealed off from the rest of the cosmos. We are hurtling through the Milky Way galaxy at over 500,000 miles per hour, constantly plowing through interstellar space, a cosmic ocean filled with the debris of other, long-dead stars and fledgling solar systems. We are surrounded by our own defensive shell, the vast, theoretical Oort cloud, a dark, cold sphere of perhaps trillions of frozen comets, barely clinging to our sun's distant gravity. Extending almost halfway to the next star system, we are, quite literally, encased in a shell of icy debris. As we move, our sun's gravity and the gravity of passing stars constantly play a cosmic game of billiards. Stars passing light years away, unseen, can gravitationally nudge these distant comets, sending them plunging on million-year journeys toward the inner solar system, where they become the spectacular, long-period comets we occasionally witness from Earth. Other times, these gentle gravitational nudges are just enough to break the sun's feeble hold, ejecting a comet entirely, flinging it out of our solar system to wander the dark void of the galaxy for eternity as a homeless, interstellar interloper. We must assume, logically, that other star systems possess similar icy shells. This implies a staggering reality. Every single day, countless comets are being lost from their home systems and captured by new ones, or simply sent wandering. The galaxy is a vast network of exchanging objects. Our solar system is not a fortress. It's a porous border, constantly being crossed by silent travelers from afar. Scientists have long predicted that thousands, perhaps tens of thousands, of these interstellar objects, ejected from their home stars, pass silently through our solar system every single day, most too small, too dark, or too fast to be detected by our current telescopes. We just had to wait, patiently, to get lucky. On October 19, 2017, our luck finally ran out. The powerful Pan-STARRS telescope in Hawaii, scanning the skies for killer asteroids, spotted a faint, fast-moving point of light. At first, astronomers classified it as a routine comet, giving it the designation C 2017 U1. But as they watched, they quickly realized something was profoundly wrong. It had no coma, no fuzzy, gaseous tail of sublimating ice and dust, which is the defining characteristic of a comet. Confused, they reclassified it as an asteroid, A 2017 U1, the first time an object had ever been reclassified in this way. But as they gathered more data and calculated its precise orbit, a shocking, history-making realization dawned. It was moving too fast, far too fast. Its trajectory was not a gentle, closed ellipse like a planet or asteroid. It was a sharp, open-ended hyperbolic curve. This meant it was not bound by our sun's immense gravity. It had come from deep interstellar space, and it was heading right back out. This was it. Our first confirmed interstellar visitor. The object was swiftly given a new, fitting Hawaiian name, Oumuamua, a word meaning first distant messenger, or scout from the dark past. The International Astronomical Union was forced to create an entirely new designation system just for this object. One I, for the first interstellar object. Scientists around the globe were ecstatic. This was our first, unprecedented chance to study a piece of another solar system, a relic from another star, up close. What was it made of? Where did it come from? But as the limited, precious data trickled in from every available telescope straining to observe the rapidly fading outbound object, the initial excitement turned to profound bewilderment. Oumuamua was not behaving like anything we had ever seen. The bewilderment began with its very nature. As telescopes strained to get a reading, they measured how its brightness changed over time. Oumuamua's brightness wasn't stable. It was pulsating dramatically, varying by a factor of 10, as it tumbled end over end roughly every 7 hours. This was not the subtle flicker of a slightly oblong asteroid. This extreme variation in brightness meant the object had an impossibly bizarre shape. To explain the data, astronomers theorized it had to be either an incredibly long, thin cigar shape, perhaps 10 times as long as it was wide, or, just as likely, a perfectly flat, pancake-like disk. Neither shape made much natural sense. We don't see asteroids or comets like this in our solar system. Such an extreme, elongated or flattened object would be structurally weak, and it's hard to imagine how it would even form, let alone survive a violent ejection from its home star system and a millions of years-long journey through interstellar space. It was also tumbling chaotically, rather than rotating smoothly along a set axis, suggesting it had a complex history, perhaps involving a collision. Adding to the oddity, its color was reddish, consistent with objects in our own outer solar system that have been space-weathered by eons of cosmic radiation. But it was also surprisingly shiny. Data from the Spitzer Space Telescope indicated it was at least 10 times more reflective than the typical tar-black comets we are used to, which are covered in dark, organic material. This high reflectivity hinted that its surface might be bright, icy, or perhaps metallic. Was it an asteroid fragment from a distant planet's collision? Or a strange, dead comet, its icy surface coated in a thick, insulating crust of interstellar dust that prevented a coma from forming? But all these fascinating, bizarre physical oddities paled in comparison to what astronomers observed in its motion as it looped around our sun. Oumuamua passed its closest point to the sun on September 9th, 2017, inside the orbit of Mercury, traveling at a blistering 87 kilometers per second. As expected, it then began its long journey back out into the void, and that's when it openly, flagrantly, broke the most fundamental law of celestial mechanics. It didn't slow down as expected. As it moved away from the sun, fighting against its immense gravity, it accelerated. The acceleration was tiny, just a small, persistent, non-gravitational push, but it was statistically significant, unambiguous, and completely undeniable. As Rob Warwick, the researcher who first spotted it, later confirmed, its motion simply could not be explained by any normal asteroid or comet orbit. Something else was actively pushing it, acting like a tiny, invisible engine. In the precise language of physics, acceleration absolutely requires a force. So, the billion-dollar question became, what was the engine? Scientists around the world scrambled for answers. The first, most obvious idea was solar radiation pressure. The sun emits a constant, high-speed stream of photons and charged particles known as the solar wind, and this stream carries momentum. Over time, it can push objects in space. We are actively using this very principle to design solar sails for advanced spacecraft. But for a normal, rocky, asteroid-like object with the estimated size and mass of Oumuamua, the push from the solar wind would be utterly negligible, thousands of times too weak to account for the observed acceleration. That hypothesis was ruled out almost immediately. With solar radiation pressure failing to explain the push, scientists turned to the next most obvious explanation: cometary outgassing. This is the standard textbook mechanism for non-gravitational acceleration in our solar system. As a comet, which is essentially a dirty snowball, gets close to the sun, its surface ices composed of water, carbon dioxide, methane, etc., heat up rapidly. They don't melt in the vacuum of space. They sublimate, turning directly from solid ice into vast clouds of gas, shooting off the surface in powerful, sun-facing jets. This violent, continuous outgassing of gas and dust is what creates a comet's spectacular signature tail and its fuzzy, glowing coma. Crucially, this one-sided venting also acts exactly like a tiny, natural rocket engine, giving the comet nucleus a gentle, persistent push away from the sun, altering its path in ways that gravity alone cannot explain. This, surely, had to be the answer. Oumuamua was simply a comet, its identity masked by its interstellar journey. There was just one massive, glaring, data-driven problem. There was no gas, there was no tail, there was no coma. Telescopes, including the immensely powerful Spitzer Space Telescope, were pointed at Oumuamua, staring at it for over 30 hours, specifically searching for the telltale infrared signature of a coma, the cloud of gas, like carbon monoxide or carbon dioxide, and dust that must accompany any significant outgassing event powerful enough to create the observed acceleration. They found nothing. Absolutely nothing. The object was completely inert, as clean as a rock, emitting no detectable heat or gas. Yet, to create the measured push, calculations showed Oumuamua would have needed to be shedding a significant fraction of its mass in material, all of which would have been easily detectable by Spitzer and other observatories. Furthermore, the Spitzer data, by constraining its temperature, reinforced that other anomaly. Oumuamua was at least 10 times shinier, more reflective than a typical comet. Comets are famously some of the darkest objects in the solar system, covered in tar-like, organic-rich, sooty material from eons of radiation, making them blacker than fresh asphalt. This object was bright, reflecting sunlight efficiently, perhaps even suggesting a shiny metallic surface. This impossible combination of contradictory facts, a high reflectivity, a bizarre, extreme physical shape, either a cigar or a pancake, and, most importantly, significant, comet-like acceleration without a visible cometary tail created a profound and deeply uncomfortable mystery for the entire astronomical community. The object simply defied all known, established categories. It looked like an asteroid, but it acted like a comet. Yet a comet with no tail, a rocket with no exhaust. The data just didn't add up. It was in this vacuum of a plausible, consistent, natural explanation that one of Harvard's most prominent and senior astronomers, Avi Loeb, stepped forward with a hypothesis so radical, so controversial, that it instantly ignited a firestorm in the scientific community and made global headlines. Loeb argued that there was one force that could account for the gentle, continuous push: simple solar radiation pressure. He argued it could provide the observed acceleration, but only under one very specific extreme condition. If Oumuamua was not a cigar-shaped rock, but was instead an object with a massive surface area and an incredibly low mass. His calculations showed it would need to be an impossibly thin, flat object, perhaps hundreds of meters long, but less than a single millimeter thick. A natural object of this extreme fragile shape, a massive, ultra-thin pancake or sheet, was seen as astronomically unlikely to form naturally, let alone survive a violent ejection from its home star system and a perilous journey across interstellar space. Therefore, Loeb proposed, invoking the principle of Occam's razor, that the simplest explanation is often the correct one. The most logical, parsimonious explanation for an object with these unique, thin sail properties was that it was artificial. It was, he suggested, a light sail, a piece of defunct or active alien technology created by an extraterrestrial civilization, designed specifically to catch stellar winds and accelerate through space, perhaps as a probe or a piece of discarded interstellar debris. He wasn't claiming it was a spaceship full of aliens, but that its properties were most consistent with an artificial, technological origin. The theory that Oumuamua was an alien light sail, proposed by the tenured chair of Harvard's astronomy department, was explosive. The media loved it. The scientific community, by and large, did not. It was a sensational, headline-grabbing claim, an explanation of absolute last resort, and most scientists felt strongly that all natural possibilities had not yet been fully exhausted. No matter how strange they might be, the race was on, not just to study the object, but to find a plausible, natural explanation for its bizarre, tailless acceleration, one that didn't involve invoking little green men and alien technology. The academic backlash against the alien hypothesis was immediate and intense. Critics argued that invoking aliens based on a single, ambiguously shaped object with anomalous motion was a severe violation of the long-standing scientific principle, often summarized as the Sagan standard, that extraordinary claims require extraordinary, irrefutable evidence. The burden of proof, they argued, was not on disproving the alien idea, but on finding any plausible natural mechanism, however exotic, that could fit the observed data. The scientific community scrambled to find one. Enter Daryl Seligman, then a postdoctoral researcher at Cornell University, who proposed a clever, if highly exotic, alternative explanation. What if the cometary outgassing was happening, but it was simply invisible?
Oumuamua.
What if the reason our powerful telescopes, including Spitzer, couldn't detect a coma was because Oumuamua wasn't outgassing water vapor, carbon dioxide, or dust? What if it was outgassing a stealth gas, something our telescopes couldn't easily see in that specific context, like pure elemental hydrogen? Seligman, along with his colleagues, proposed the novel idea that Oumuamua was, in fact, a hydrogen iceberg, a massive frozen chunk of solid molecular hydrogen. Such an object, they theorized, could potentially form in the absolute coldest, densest regions of interstellar space, perhaps deep within a giant molecular cloud, the birthplace of stars. As this hypothetical hydrogen iceberg passed close to our sun, the gentle warmth, even at that distance, would be more than enough to cause the solid hydrogen to sublimate rapidly, turning directly into vast quantities of invisible hydrogen gas. This massive invisible outgassing would act exactly like a powerful, stealthy rocket engine, providing the precise, non-gravitational push that was observed, all without creating a visible dust tail or a coma detectable by Spitzer. It was, at first glance, a brilliant and elegant theory. It neatly explained both the mysterious acceleration and the perplexing lack of a visible coma. It provided the perfect natural explanation to counter the sensational alien light sail hypothesis. But Avi Loeb, the lead proponent of the artificial origin, disagreed intensely. Just a few months later, he and a colleague co-authored a stinging counterpaper. They demonstrated, using detailed mathematical models, that a hydrogen iceberg, even one formed in the nearest, densest molecular cloud, simply couldn't survive the long, arduous journey through interstellar space. The faint ambient starlight and cosmic radiation in the interstellar vacuum, Loeb and his co-author argued, was itself warm enough that it would have completely sublimated, or melted, any solid hydrogen iceberg in a relatively short amount of astronomical time, long before it ever had a chance to reach our solar system. The hydrogen iceberg theory, while elegant, appeared to be physically non-viable, just as fragile as the light sail it sought to replace. Loeb's refutation was powerful. Loeb's powerful refutation sent Seligman and his colleagues back to the drawing board. They had to concede that the pure hydrogen iceberg idea, while clever, likely wouldn't work. However, Seligman remained fascinated by the core concept of invisible hydrogen outgassing. The problem wasn't necessarily the gas itself, it was the source. How could you get pure hydrogen gas to be released from a solid, comet-like object, if not from a pure, fragile hydrogen iceberg? The crucial breakthrough came in 2023, when Seligman collaborated with Jennifer Bergner, an assistant professor and astrochemist at the University of California, Berkeley. Bergner, an expert in laboratory ice experiments that simulate deep space conditions, pointed to a known, well-documented phenomenon. When common water ice, H2O, the most plentiful ice in the universe, is formed in extremely cold, deep space conditions, and is then bombarded for millions or billions of years by high-energy cosmic radiation, which is everywhere in the interstellar void, something amazing and counterintuitive happens. The radiation can penetrate the ice, break apart the water molecules, and create and trap pockets of pure, molecular hydrogen gas, H2, inside the otherwise solid water ice crystal structure. Later, if this radiation-baked water ice is gently warmed, for instance, by passing near a star like our Sun, the ice structure subtly rearranges itself, releasing the trapped, invisible hydrogen gas long before the water ice itself gets warm enough to sublimate significantly. This didn't require a fragile, exotic hydrogen iceberg at all. It only required a standard, boring, water ice comet that had simply spent a very, very long time traveling through interstellar space, getting thoroughly baked by cosmic radiation. This new dark comet, or water ice hypothesis, was a revelation. It seemed to account for everything perfectly. The comet-like acceleration came from the invisible hydrogen gas escaping as the ice warmed and rearranged, and the lack of a visible tail was also explained, as this process releases pure hydrogen gas, not the vast quantities of dust and other volatile compounds like CO2 that are violently ejected from a typical comet's surface and create its dusty, visible coma. It was, to date, the most complete, physically plausible, natural explanation yet proposed, and it gained significant traction within the scientific community. While this was still not enough to completely convince Avi Loeb, who quickly co-authored more papers arguing against the precise mathematics of the new dark comet theory, while continuing to assert that the alien light sail model remained a more probable and simpler explanation, Seligman's new idea had opened a fascinating and crucial new line of inquiry. If Oumuamua was a dark comet, releasing trapped hydrogen, could there be other dark comets out there? Not just rare interstellar visitors, but perhaps objects lurking, hidden, masquerading as asteroids within our own solar system? Seligman and his colleagues began a new search, not of the skies, but of existing astronomical data. They pored through orbital databases, looking for any known solar system objects, currently classified as asteroids or comets, that showed tiny, persistent, non-gravitational acceleration that could not be explained by any other known mechanism, like solar wind, thermal effects, or, crucially, any visible outgassing. Their painstaking search was successful. They found six small, seemingly unremarkable objects, already cataloged but largely ignored, all orbiting relatively near Earth objects. Some were incredibly tiny, just a few meters across. On all our telescopes, they looked like simple, inert asteroids. They displayed no visible comas or tails. Yet, their meticulously tracked orbits showed tiny, inexplicable accelerations, just like Oumuamua. They were not interstellar, not zipping around like alien spaceships, but their motion was, according to our current understanding of physics, wrong. They were, perhaps, a local population of these dark comets. This was a critical discovery, as it provided a testable prediction, a way to potentially validate the theory. The discovery of 6 dark comet candidates, already lurking within our own solar system, was a potential game changer. It meant that this strange phenomenon, this tailless acceleration, might not be a one-off interstellar anomaly, but a new, previously unrecognized class of celestial object. Intriguingly, one of these 6 anomalous objects, a small, fast-rotating asteroid named 1998 KY26, was already the scheduled target for an extended mission by JAXA's, the Japanese space agency's, Hayabusa 2 probe. This brilliant sample return mission, having successfully completed its primary objective at asteroid Ryugu, was now using its remaining fuel to embark on a long journey to this new target. With a planned high-speed flyby in the year 2031, scientists would soon get an up-close, direct look at one of these mystery objects. If Hayabusa 2's sensitive instruments detect evidence of invisible hydrogen outgassing as it approaches, the dark comet theory will gain massive, perhaps definitive support. If not, the mystery deepens. While this provided a path forward, it still didn't definitively solve the Oumuamua debate. Meanwhile, our solar system had already been visited again. In 2019, a second object from beyond, 2I, Borisov, was detected, this time by an amateur astronomer. Borisov was completely different from Oumuamua. It was, unmistakably, a comet. It had a massive, brilliantly visible coma and a long, dusty tail, which at its peak stretched 14 times the size of Earth. It looked, and more importantly, acted exactly as physics predicted a comet should, showing only the expected, conventional outgassing. Borisov, in its normalcy, served only to highlight how truly bizarre, how unique, how anomalous Oumuamua really was. Other objects, too, hint at the constant interstellar exchange. Comets like Mahol's one are believed to be captured interstellar visitors from long ago. Conversely, our own comet C, 1980 E1, was gravitationally ejected by Jupiter in 1980, destined to become an Oumuamua for another star system. The galaxy is a vast network of exchanging objects, but none of this answered the central questions. Where did Oumuamua come from, and what was it? Astronomers traced its path back towards the star Vega, but identifying a home star is nearly impossible over its millions of years journey. Now, it is billions of kilometers away, too faint to see, its secrets lost to the void. This frustrating lack of data has led some, like Project Lyra, to propose the unthinkable, launching a high-speed probe to chase it down, a mission that could take decades, using complex gravity assists from Earth, Venus, and Jupiter to build up enough speed. Is it worth the immense cost? Or, as astrobiologist Karen Meach suggests, should we simply wait for the next one? New observatories, like the Vera C. Rubin telescope, are predicted to find dozens of interstellar objects per year, spotting them before they pass the sun, giving us time to study them. ESA's Comet Interceptor, 2029, will park in space, waiting to ambush the next pristine visitor. But these missions won't give us data on one eye, Oumuamua itself. Its unique, bizarre secrets, whatever they were, are being lost forever to the void. Ultimately, we are left with tantalizing, unproven theories. Was it a dark comet? A new class of object? Was it an alien light sail? Or something else entirely? Without more data, we simply do not know. That is the wonder and the agony of science. What other cosmic mysteries or strange phenomena do you want us to investigate? What do you think Oumuamua was? Let us know your theories and ideas in the comments below. If this journey to the edge of our solar system sparked your curiosity, please like this video, share it with fellow explorers, and subscribe for more deep dives into the great cosmic unknown. Keep looking up. Keep questioning.